All right, in our last lesson, we covered this design rule. Oh, okay, thanks. We covered this design rule about sizing the circuit breaker for motor, okay? And why do we need a special design rule for a motor? Because motor has a very special characteristics. When we try to start it, it will have a very high current, which looks like this. Okay, this is current, this is time. And so we have a device which we call the motor starter to bring down the starting current. Okay, two function. One, to lower the starting current, and another function to provide overload overload protection. Okay, why do we need so? Because we know that the circuit breaker that we have only provide short circuit protection. Okay, and how do we size this circuit breaker? We consider the starting method, which I mentioned that everyone should be familiar with star delta and also direct online. So if we are using a star delta starter, we take the full load current IFL multiply by 2. We get our design current, which we call IB, and we select a circuit breaker IN, which is either bigger or equals to IB. All right, so today we will extend this concept to a group of motors. Okay, last week we looked at single. Today we will extend to a group. And so here we are. We have a group of motor. Okay, and we are interested to size this circuit breaker, which is going to protect what we call the feeder. Okay, so the feeder is this. Essentially, it is just a cable that fits Okay, so we use the term feeder because the cable that feeds the group of motor. Yeah, this is one of the technical jargons that you may hear next time in future. Feeder. We are interested to be able to determine the size of this. And of course, before we do that, we need to know what is IB, the design current. All right, so to differentiate between IB here and IB here, we use IB prime for the feeder circuit. And similarly, we will use IM prime for the feeder circuit breaker. All right, so nothing new to you if we are interested in the maximum demand of this group of motors, right? Basically, it will be just all the full load current. So this is the expression. It is basically just the full load current of the largest motor plus the rest. Okay, quite intuitive. So like what we have done in our residential design, sometimes we will apply what we call the diversity factor. Correct? So if we have a group of motor and we expect some of them not to be running, we can then apply diversity factor. Okay. So what are the contexts in which motors may or may not be running all the time? Just want to quickly show you this chart. Okay. So for example, in a factory, we have, let's say, 3 conveyor system. So 1, 2, and 3. And we know, let's say, our output is 30,000 face masks. Okay. If we run all the 3 conveyors together, right? But this factory, for most of the time, is only able to sell 20,000 face masks. Okay, let's say in a month. Meaning to say is that the factory will most likely be operating only 2 conveyor in a month to produce what the factory can sell, right? There's no point to run all 3 conveyor system and to produce this amount and then you keep stocking up. Okay, so there is some spare capacity here. And that is when diversity will comes in. Okay? While we have 3 of them, we do not run all 3 of the motors at the same time. Okay, so the third spare machine could be for maintenance use. So when we are maintaining machine 1, we will run 2 and 3. While we are maintaining 2, we will run 1 and 3. Or it could be for times of emergency when one of the system break down. Okay, of course, this spare could also be used to ramp up production as and when needed. Okay, and that's where we can apply diversity factor. So there are cases that we do not allow diversity factors. Okay, in another factory. Okay. Yeah. Same 3 conveyor system. But each conveyor system, instead of being able to produce 10,000, can probably only produce 8,000 pieces of face masks. Okay. And this factory is able to sell, let's say, 25,000 pieces a month. And in this context, of course, we know that we will have to run all 3 machines to be able to meet or barely meet what the factory can sell so that we can maximize our profit. Okay, so in this case, we do not allow diversity. And hence, to really know the situation or when we can or we don't apply diversity, it will really require your knowledge and experience of the type of installation that you're working with. But for the purpose of test and assessment, we will be explicit. If we need you to apply diversity, okay, we will say so. If we don't need you to apply diversity, we will say that, yeah, diversity is not allowed. Okay. And where can we find a good reference of how to apply the diversity factor? We can refer back to our favorite table DF, diversity factor, which can be found in the OCP. So table DF. And now we are looking at small shop, stores, and office premises. Okay, in the past, we are looking at this when we do residential design. But now we have moved on to the context of office and factory. Okay. So we look under row number 4. We have the diversity factors that says 100% full load of the largest motor, followed by 80% of the second largest and 60% of the remaining motors. Okay, so we take this 100, 80, and 60. Okay, so we go on first to see how we can apply this. A good example here. Okay, we have this system in which we have 3 numbers of M1 kind of motors. So we have this group. Okay. And then we have another group that is M2. And we have the third group, which is M3. Okay. So a key thing to remember that when we apply diversity factors for motors, we apply it to motors of similar type. Okay. Or in the same group. Okay. In this case, if we are not going to apply diversity, okay, just want to highlight here, no diversity allowed, all loads are running at all time. So we will have 100% of all the full load current. And if we were to apply the diversity factor from table DF, it will look like this. Okay, so table DF, okay, and then we apply it to the same motors of the same group. So we have 100% of the largest. So in this case, all the motors have the same rating. They're all 100 amps. Okay, so there isn't really a distinction. So we take 100% of the first one, followed by 80% of the second one, and then 60% of the third one. Okay, and if we continue to do this, we are going to apply diversity factor to the second group again. So we have to start with 100% and 80%. Okay, so it is not correct to say that this is 60%, this is 60%. Because M1 and M2 are of a different group, and so we do not apply diversity across different groups. So rather than taking that this is 60%, because these are the remaining, we have to start at 100% again. So just take note that we have to start at 100% again. And the next one will be 80%. So in the same principle, when we come to the third group of M3, we restart at 100% and the next one will be 80%. I stop here for 10 seconds to let you internalize this concept about diversity for motors before we go back to sizing the feeder circuit breaker. Okay. Any question? So the idea about maximum demand is same as what we have done in topic 2. Okay. So is the idea of diversity factor. What is new today is how do we apply the recommended diversity factor to different group of motors as shown here. So I will wait for questions, if any. Okay, no question. Then let's go back to where we have started. We are interested to know the method or design process to size the circuit breaker for the feeder. And we know that the idea of maximum demand is the same. So in this case, if we need to apply diversity factor, the maximum demand expression will looks like this: 100% I full load largest motor, okay, plus 80% I full load second largest machine, plus 60% I full load of rest of machines. So we are good, but we also know from our last week experience that knowing this maximum demand, which I may call it IMD, cannot help us to size our breaker because of the motor starting current, right? So instead of using IMD, we have to use the design current, IB prime, to help us select our circuit breaker. Okay, so we still use this rule. Okay, circuit breaker size must be greater or equals to IB prime. And what is our IB prime now? Okay, instead of using the full load current of the largest motor, all we need to do is to swap this expression with the circuit breaker rating. Okay. So repeat again, instead of using the full load current, we will swap this expression with the circuit breaker rating size of the largest motor. So keep this in mind while we look at an example. So we have this example, example 9. we have a group of motors and all of them are identical. Okay, so the keyword here, identical. Okay, so meaning to say is that we can infer that they belongs to the same group. All right. And we all use direct online starter. So if you see direct online, then you have to remember that the factor is 2.5. To calculate, when we calculate IB for single and we need to determine the maximum demand and incoming circuit breaker. Okay, so we also call this the incoming. We also call this the incomer. We also call this the feeder. Okay, so we are interested to find the IMD here. We are interested to find what is the size of this. And of course, in the process, we need to find IB prime. So usual, we need to find out what is the breaker or the full load current of each motor first. And this is straightforward. We have done this before. The only thing that I want to highlight is that this is given in horsepower. You need to remember this 1 horsepower equals to 746 watt. We are using single phase. So single phase implies the voltage is 230. Full load current will be P over V over power factor over efficiency. And we end up with this. Okay, and then we use a direct online starter. So we multiply by full load. We multiply full load current by 2.5 to get our design current 15.9 amps. Okay. And as a recap, we then select 20. Okay. Yeah. We may not be using 16 because 16 is now not so common on the market. So we will select 20. So this is a quick recap. I don't think there is much of an issue. So now that we get this, yeah, why do we need to get this? Because remember in our IB prime, we actually need circuit breaker size of the largest motor. Okay, so since they are all identical, we need to at least find the circuit breaker for one of them. All right. So to put the diversity factor concept into practice, now we need to determine maximum demand. We know that we first have to take 100% of the largest motor. They are identical, so it doesn't matter. So your maximum demand will be 6.36 for the first largest one. And then 80% of the second largest. Okay. So in this case, identical, so no issue. We remember to multiply by a factor of 0.8. And after taking out the first two, so we have one, two, we are left with 4 of them, right? So the remaining motors will be at 60%, 0.6, and there are only 4 of them. So multiply by 4 and multiply by the full load current. we end up with this 26.71. Okay, so this is the maximum demand. Okay. For circuits with motor, we know that we can't use the maximum demand to size the breaker. So we have to move on to the next part where we do calculations for the design current IB prime here. Okay. So all we need to do is, instead of using 6.36 here, right, we take away and then we replace by 20. And where do we get 20? 20 is actually the circuit breaker size. All right, and we end up with 40.34, and hence we select the next biggest one, which is 50. That is how we are going to apply this design rule that we introduced today. Any question at this point?